finishing that last bit of content from last time's notes. So let's begin by just remembering how to find global and local mins and maxes. So if you remember a global max, it's the largest y value you see on a graph. It's the largest output that a function produces. And if you want the input that produces the global max, just give me the x value that gives you that y value. So let's maybe even just go back to, you could look at a computer-generated plot, but let's actually just look at this plot. So there's the graph of y equal to x cubed minus 4x on the interval from -2 to 2. Tell me, what is the maximum value of that function on that interval? 3? Yeah, that looks like 3. What x value produces it? X equals -1.2. So we have a global max of 3 attained at x approximately equal to -1.2. That makes sense? Let's also ask for a local maxima. On that graph, do you see any local maxes? Yeah, how about that one that we just found that was a global max? It was a global max, so certainly it's a local max. Let's see how that would change if we tweak the problem just a little bit. So I'm going to pull up a computer-generated graph now. Oh, come on. Let's plot that same function. X cubed minus 4x. But this time let's go from x equals -3 to x equals +3. Just see how it changes. So let's zoom in and make that a little bit more visible. So just by looking at that graph, does that still have a global maximum at y equals 3? Is 3 the largest y value you see on the graph? No. So this now has a global maximum not at 3, but of, I don't know, closer to 15? Attained at x equals 3? So changing the domain can change global maxes. So over -3 to 3, it seems like the global max changes. But let's ask, by looking at this graph, does it still have a local max at the same place where it used to have a local max? So local maxima only see a local bit of the domain, so making the domain bigger won't change any local behavior. That makes sense? Nice. And endpoints, we'll never call them local maxes or mins because we can't see what's going on beyond. It could keep increasing, or it could turn around at that endpoint. You can't tell. Let's think about another one. Let's try to maximize f of x equal to 1 over x. And let's start by looking at an actual graph. So let's plot 1 over x, and sure, that domain will do to begin with. Because from there you can see the pattern that is how the graph behaves in general. Looking at this graph, is there a single y value which is bigger than every other y value that will be on the graph? Well, here it looks like that's the maximum, but does it actually attain a value that's bigger than that? Yeah, a little bit closer to 0 would get bigger. So this doesn't attain any maxima. So if you plot y equals 1 over x, you'll get a graph that looks... Oh, you can't see that. I didn't switch back. You'll get a graph that looks something like this. So if you'll see, there are no maxes and no mins. In fact, does it have any local maxima? It also doesn't have any local minima. So some functions can behave badly and not have any extrema. Let's do one last one, and I think I'm going to skip finding maxima and minima because I want to introduce a new one. I want to introduce the average rate of change. So let's suppose someone gave you this function from that graph and asked you, on average, what's the function's rate of change from x equals -2 to x equals 3? Well, to do that, you would say, well, how much does it change from x equals -2 to x equals 3? And you would divide by, well, what's the difference between -2 and 3? So let's do that. And well, maybe we'll even do it graphically first. So from -2, it looks like it goes through -2 comma 2 to 3, 1, 2, 3. Looks like that's somewhere around 3 comma -1.5. If you wanted to find the average rate of change between those 2 points, well, that would just be how much does the function change divided by how much does x change. So let's do that. So it would be f of 3 minus f of -2 all over 3 minus -2. And we know what all of these values are. According to this graph, what is f of 3? -1.5. What's f of -2? 2. 3 minus -2, I think, is 5. So it'll be whatever -1.5 minus 2 divided by 5 is. So that's -3.5 divided by 5. And I think that's the same as -0.7. That computation make sense? And let's go ahead and just take a look at that also visually. So that's the same thing as, right, we took how far up or down did the graph go and divided it by how far left or right did the graph go. That's the same as like the slope of that line. So the average rate of change of a function, also known as the average slope of the function or the slope of the secant line of a function, over some interval a comma b, is given by the change in the function divided by the change in x, or if you prefer, the change in y divided by the change in x, or given by rise over r1, is just f of b minus f of a all over b minus a. That definition make sense? Let's use it to make a single computation. Let's take f of x equal to x squared plus 1 and find its average rate of change over the interval 1 comma 2. Okay. I think I'm going to pause for a second and sip my coffee, and you guys will compute that using this definition. check with someone next to you. See if it seems reasonable. If you and someone else got the same number, then chances are it's believable. So what is that average rate of change from 1 to 2? 3 idea? And I'm not going to compute it again. I mean, is there a demand that people want me to write down a computation? Okay, yeah. Then I will do it. So let's do it. That is why I ask. So if we want to compute the average rate of change over this interval, all right, what do we need to do? We need to compute f of b minus f of a all over b minus a. Fair enough. The fact that I've already written the theory right there is going to get in my way, but that's all right. What do you get when you plug in x equals 2 to the function? 5. Because you'll get 2 squared plus 1. 2 squared is 4, plus 1 is 5. 5, and I'll even color code this f of 2 is that 5. Minus, what do you get when you plug in x equals 1? 2, I think. 2. And then you need to divide by 2 minus 1, but 2 minus 1 I think is just 1. So I wind up with 5 minus 2 all over 1. 5 minus 2 is equal to 3, I guess. And 3 divided by 1, well, division by 1 is the easiest thing to do, so that is just 3. Was that helpful? Good. So maybe I'll take just a moment and also give a sales pitch for the extra credit which is on the reverse side of this document. So it advertises a calculus concept, namely the instantaneous rate of change. Let's see, how many people, because I know that the background in this class is always very diverse. If I say the word derivative, how many people already have an idea what that means? All right, this is going to have you go through a computation of the derivative, though I won't mention the word derivative. So that average rate of change definitely depends on what 2 points you pick. And generally speaking, you don't want the average rate of change between 2 points. You would really much rather say, well, what is the actual honest-to-God rate of change at a single point? You can look at this graph and see, oh, well, like, I see, like, that slope. What is that slope? How can you compute it? And, well, what do you do if you want to compute it? That seems to be the slope from right at x equals 3. Well, you compute the slope from x equals 3 to x equals 2, a number that's really, really close to 3. But that still won't give you that exact slope. But if you take that number and make it really, really close to 3, you'll get something that hopefully is getting close to a number. That thing is called the instantaneous rate of change, and you'll do that on the next page. So take a look at that, do some computations, come talk to me on your own time. People have any questions at all? Possibly about how the extra credit works? Yeah.
So it's literally just taking the derivative of it?
Yep.
Okay.
I mean, don't say just. It's taking the derivative. And you might know these handy formulas to compute derivatives of polynomials, but don't use them. Yeah. Because I want to actually see you computing rates of change. You can use the fact that you know them to know what the answer should be in advance. Cool. So let's actually start in on the content that I wanted to start today. So maybe I said this before. So those of you who like to start the homework as soon as it's assigned might wind up starting the homework before I remove the problems that reflect content that we don't quite make it to. So the homework assignment may get shorter sometime later today. No problems will be added, problems will only be removed, and there will only be problems corresponding to today. So there are 2 goals that I have in this note packet. I want to start by just giving you a bucket of functions that are functions whose graphs you should just have in your head at all times. My second goal is if you have all of these functions whose graphs you just know, what are some basic transformations we can do to these functions to get more functions, and what do those transformations do to graphs? Those are the goals for today, and Monday also. So let's start by here are some reasonably simple functions. Y equals x, y equals x squared, y equals x cubed, y equals x to the fourth, and then we'll keep on going beyond that. And in order to get an idea what the graphs look like, we'll use a computer for some of them, but one of them, you just know. What does the graph of y equals x look like? It's like a straight line through the origin, slope 1. So let's go ahead and draw it. So I think I'm going to put the odd ones here. So there's the graph of y equals x. And what do you think? I put that in the column of odd functions. By looking at that graph, is that an odd function? Does it have symmetry across the origin? Yeah. So it actually belongs in that column, though that column was mislabeled. Let's start looking at graphs of the remaining ones. So let's plot, and I mean, we've looked at graphs like this by plugging in points once, but let's just get a computer-generated graph. So there's the graph of y equals x squared. It's roughly, I don't know, bowl-shaped, I guess you would describe it as. You might even say parabolic, though if you don't know what the word parabola already means, it means that shape. Would you call that function even or odd? Even. So there's the graph of y equals x squared. But so I just added that graph to the notes. The next one, well, maybe you notice a pattern and you think this might be an odd function, but let's actually see. Sketch the graph of y equals x cubed. Does that look like an odd function? Yeah. And in fact, maybe I'll even draw the graph of what I think y equals x to the fourth should look like before we even graph it. I think it'll look an awful lot like y equals x squared. And let's just check that. So I am recording this lecture, but I'm only recording the stuff that the document camera sees. So if you go and you review this lecture online, this bit will seem very silly. And yeah, so there we see the graph of y equals x to the fourth. It looks about like the graph of y equals x squared. And I don't know, let's see if we can't notice something a little bit further. So it looks at a glance maybe like even powers of x result in even functions. And that makes sense, right? Even powers can't tell if you multiply x by -1. Odd powers of x seem to result in odd functions, which again makes sense. You have an odd number of x's multiplied together. You can pull out a single negative sign. That's exactly what it means to be odd. Let's just look at all of the graphs and see if we can make any other qualitative statements. So let's sketch the graph of a bunch of odd powers of x. X cubed, x to the fifth, x to the seventh, x to the ninth. And let's maybe even, there, that's probably, Chris. So there are the graphs of the lot of them. So I guess qualitatively, do those all look very similar? And it looks like as the power goes up, it gets flatter close to 0, but then steeper farther away from 0. So there's a nice local observation to make. Let's look at all of the even powers. Squared fourth. There. Qualitatively, do they all look similar? And they all, again, keep getting flatter closer to 0, steeper farther away from 0. And that's this qualitative description that I'm looking for. So we want, in fact, anything that looks like x to the odd will always look qualitatively something like this. Anything that looks like x to the even will always qualitatively look something like this. Feel okay about that? And that's only held up when looking at those graphs. So let's answer some questions just based on this picture. All of that was super qualitative, so maybe you'll be surprised that we can get any sort of concrete information out of it. Where are the x-intercepts of these functions? At 0, 0, at y equals 0. Where are the y-intercepts? Same. So x-intercept, comma y-intercept, both at the point 0, comma 0. And now I'll split it into odd case and even case. So look at all of the odd powers of x. That gives the generic picture. Where would you say that function is increasing?
Positives.
Nope, you answered it for evens, for the even powers. I said odd, right? Did I say odd? Okay. But that answers a question. So even functions seem to be increasing when x is positive, or I guess the other way of writing that would be from 0 to infinity. But what about odd functions? Where do they seem to be increasing? The things that look like x to the odd. Well, maybe a better question is, where do they look like they're decreasing? No. The things that look like x to the odd are decreasing never. So they're increasing from negative infinity to infinity. How many people would want to say that they're not increasing when x equals 0?
Can you move it up a little?
Oh, yeah. Oh, yeah, the red line that says it's recording is speeding up that bit of screen. So that question now, how many people would want to say that these things are not increasing when x is equal to 0? I guess, okay, so no one. Yeah. It would be reasonable to say that, but if you look close to 0, the definition of increasing is just as x goes from left to right, y goes up. And it still does that close to 0. It just slows down a lot. So things that look like x to the even, if they were increasing when x is less than 0, they must be decreasing when x is, I said the wrong thing. When x is less than 0, they are decreasing, also known as the interval from negative infinity to 0. All functions that look like x to the even really just look kind of like x squared. All functions that happen to be of the form x to the odd qualitatively look like x cubed. I guess as long as that odd number is bigger than 1. X to the power 1 really does look different. It doesn't have that wiggliness. So there's the first bunch of functions that are now in your toolkit of functions that you should just know. If I ask you for the graph of x to the 6th, you should be able to qualitatively draw a graph without doing anything. Well, here's the next bunch. Let's talk about nth roots. So let's see. Let's think about what well, we've seen the graph of y equal to the square root of x, but let's see why the function y equal to the square root of x looks like it looks. So let's take that equation, y equals the square root of x. Could you rewrite that so that x is a function of y? Could you solve that for x?
X equals to y squared.
X is y squared. Oh, cool. So that is basically the same graph as y is equal to x squared, but the x's and y's are flip-flopped. So let's copy down the graph of y equals x squared, but with x's and y's flip-flopped. And I'm doing it in dashed because I'll want to not use this graph. Is that the graph of a function?
No.
it's not. So something here went wrong. And let's look at it. So it looks like there's this issue with you have a positive and negative choice of y for every x value. Is the square root function ever negative? No. So there's the constraint. So y is equal to the square root of x is given by the equation x is equal to y squared with y bigger than or equal to 0. So we're just going to throw out all of the negative y values. And there we have the graph of y equals the square root of x. That seem okay? Let's do the same thing for the next power law. Let's try to sketch the graph of the cube root of x. And we'll go through the exact same motions, maybe faster. So how would you rewrite y equal to the cube root of x so that x is a function of y? What would you get?
X equal to 3 cubed.
Yeah. X is equal to y cubed is what you would get. So let's sketch the graph of that function. So that should look exactly the same as y is equal to x cubed, but I'll interchange the x's and y's. So instead of something that comes in like this and down like that, it'll be something that does the same, but with the x's and y's switched. So there's the graph of the cube root of x, and let's just do a quick sanity check. Is that actually the graph of a function? Passes the vertical line test. Odd roots are slightly less complicated than even roots. They have domain everything instead of just positive things. You can do the same thing for bigger powers. If you want to sketch the graph of the fourth root of x, think about graphing y equal to x to the fourth, but flipped so that y's and x's are interchanged. So there's the graph of y equals x to the fourth. No, x equals y to the fourth. Is that the graph of a function? No, fails the vertical line test. So you do the same thing. We'll only take the positive branch. Do you think we could do something similar to sketch the graph of the fifth root of x? Yeah, of course we can. Everyone feel pretty okay about that? So let's see. So in fact, this could be any. This really could be any even number root of x. This really could be any odd root of x. And so let's answer some questions. Let's ask about even roots of x, odd roots of x. And let's ask questions about where these things are, whether they're even or odd, what their intercepts are, where they're decreasing, where they're increasing. So let's start with even or odd. An even root of x, so there's a graph of it up there. Is an even root of x an even function? Folks for yes? Folks for no? Yeah, they're not, right? Because they don't even have the right domain. So the graph of anything that looks like y equals an even root of x.
Move it up a little.
Oh,
Thank you.
thank you. Will always look something like that. And if you want to ask if this is an even function, you need to ask, if I flip that over the y-axis, do I get the same graph? And you don't. If you take this point and flip it over the y-axis, you land over there, you get a point that is not on the graph of the original function. Same question is, so there's the graph of y equals x, an even root of x. Is that an odd function? No, for the same reason, right? I can take a point on this graph, flip it over the y-axis, and I get another point that's not on the graph. Any function of the form y equal to an odd root of x, well, we've seen those graphs. Those will all look something like this. And let's ask the same questions. Is that function odd? It seems to be odd. Is it even? No. Well, I told you that there's only one function that's both even and odd, and sometimes you just told me what it was, and it's not that function. So it can't possibly be even. So this is an odd function. Tell me, where are the intercepts of these graphs? At the origin. It doesn't matter whether it has x or y intercepts. It's 0, 0 either way. Where is a function of the form x to an even power increasing? Yes, hit under that. From 0 to infinity. Right, because it's not even defined when x is less than 0. Oh, okay. Increasing from 0 to infinity, decreasing never. Thank you for asking the question that I asked instead of the one that was written. What about x to an odd power? Where is that function increasing?
To 0 to infinity?
Everywhere. No, not 0 to infinity. Everywhere, right? This function is everywhere increasing? Increasing from negative infinity to infinity. Decreasing also never. People feel pretty okay? So there's now two buckets of functions whose graphs you should just know immediately. And there's one other that I just want to remind you that you know. The piecewise function y equal to the absolute value of x, which is given by x when x is bigger than 0, 0 when x equals 0, and negative x when x is negative. And we've seen its graph already. Its graph looks, well, like a wedge built out of y equals negative x and y equal to x. So there's now a pool of functions whose graphs you know. You now know the graph of every power function, every root function, and the absolute value function. And that's only interesting and useful if you can take those functions and use them to build other interesting functions. And we'll start it on the process by seeing what we should do if we want to take a function whose graph we know, add a constant to it, subtract a constant from it, add a constant to its input, subtract a constant from its input. And let's just see if people have intuition. So if you know what the graph of y equal f of x, how that looks, what do you think should change if you add a constant to that function?
It's going to move C units to the right.
It's going to move it
C units to the right.
C units to the right. Let's see what happens in practice. So let's use a computer to help us get some intuition. Let's sketch a graph of a function that we know. Y equals x squared. let's also sketch the graph of y equal to x squared plus 2. And just for completeness, let's also do y equal to x squared minus 2, just to see what those will do to graphs. So I'm going to pull up those graphs. Let's click. Sketch the graph of y equal to x squared and y equal to x squared plus 2, and see what happens. So let's see, the blue one is the graph of y equals x squared. There's the graph of y equals x squared plus 2. How does the blue graph differ from the red graph?
So it's 2 plus 2.
It's shifted by 2 in which direction? Up. So, and what do you think? Did that depend on the fact that we started with x squared? Do you think that would happen all the time? And maybe I'll take a moment and try to convince you that that should be the case. So if you take a function and add a constant to the whole function, you get that graph by shifting the graph of y equals f of x up by c. And, well, let's talk about why that happens. So remember, the y value in the graph, that's like the value of the function, that's the output. If you add 2 to a function, you just increased all of the outputs by 2. So all of the y values should go up by 2. That's exactly what moving up by 2 monetarily means. What do you think will happen if I subtract c from a function?
It goes down.
It should go down. Oh, and the constant is not 2 right now. The constant is some number c. What if instead I add c to the x value, to the parameter, x inside of the function? What do you think that should do?
There's x to the right.
I hear a lot of shift 2 to the right. That makes sense, right? You added you added a constant c to the x to c. Yeah, that makes some sense. Let's see if it works out in practice. So let's see. There's the graph of x squared, and let's also just add 2 directly to x. X plus 2 squared. Yeah, that's okay. So here's the graph of x squared. Here's the graph of x plus 2 squared. How do you shift the blue graph to get the pink graph? Yeah, say it louder then.
Solve for x instead of the parentheses.
No, I don't want to see like where they're equal. I want to know if looking at this blue graph, how could I transform this blue graph to the pink graph? Shift it by how much? By 2 to the left, or by negative 2, I guess would be the right convention. But wait, that's the exact opposite of what you told me was intuitively the right thing to do. And this is actually the correct thing to do. The correct thing to do, if you want to sketch the graph of f of x plus c, you shift left by c. If you subtract c, then you shift right by c. And there is a good intuitive way of seeing that. But kind of the moral of that good intuitive way is whenever you do things inside of the parentheses to a function, you wind up doing the exact opposite of what your intuition tells you to. If you look at it and say, oh, I have to shift to the right, then you have to shift to the left. That makes sense? And there is a good reason, but let's Oh, I guess I was supposed to copy these graphs down when I render them. So y equals x squared, we know what that looks like. It looks something like this. If I want y equal to x plus 2 squared, apparently it should be shifted 2 units to the left. So let's just track a single point. So this intercept of y equals x squared was at 0, 0. Where will that focal point go when I shift it 2 to the left? Negative 2, 0. And maybe we can go ahead and check that, because that'll actually tell us a lot. Let's plug in x equals negative 2 to this function and see if we actually get 0. Let's see, when you plug in negative 2 to the form x, plus 2 and minus 2 will cancel down to 0. You'll get 0 squared is 0. So yeah, it goes through that point. And if you think about what we just did, that I think will help a lot to build that intuition. And let's also, just to see if it actually works, sketch the graph of x minus 2 quantity squared. So what should I do to the graph of x squared to get the graph of x minus 2 squared? I should move it to the right by 2. I think I heard 3 people all say that at different points in the sentence. And so let's see, where will this x-intercept of that be? 2, 0. And let's just do the same quick sanity check. If I plug x equals 2 into that function, do I actually get 0? Yeah. Now, of course, you can do multiple of these transformations to a single thing. Let's try to go from the graph of y equals the square root of x to y equals the square root of x minus 2 plus 1. And maybe we'll even do a domain check at the end to see if this is correct. So if you want to start with y equals the square root of x, and as we progress, we'll do more of these transformations all at once. Let's try to just do one thing at a time. So if I want to go from the graph of y equals root x to the y equals the square root of x plus 1, I need to deal with the plus 1 and I need to deal with the minus 2. And I don't know, let's deal with the plus 1. What will that plus 1 do to the graph? It'll shift everything up by 1. So let's sketch that graph first. Root x plus 1. Apparently the whole thing should go up by 1, so let's do that. Everything will be shifted up by 1, and let's label this point. That point came from the point 0, 0. So where should that point with an arrow next to it? Where is that point? 0, 1. I've increased the y value by 1. The next thing I see is I still need to deal with that minus 2 inside of the parentheses. And that minus 2 is next to the only x in the function. So all of the x's, all one of them, have a minus 2 next to them. So what does that do to the graph? Shifts it 2 to the right. So this point, which is right now at 0, 1, is now at the point 2, comma 1. And from there, I see the same square root function, but shifted. And let's do, just for the sake of a sanity check, by looking at this graph, what is the domain of that function? Let's do the same thing and check the domain of this function. So let's now analytically and so that's like what x values make sense in that formula. And so when you look at that formula, I don't know, is that plus 1 going to change anything? Yeah, there's nothing I can't add 1 to. What things can I take the square root of? Non-negative things? I can't take the square root of a negative. That would be bad. So the domain of this is all of the x values for which the thing inside of the square root is non-negative. So to find that domain, I need to solve x minus 2 is bigger than or equal to 0. What's the solution to that inequality? Oh, hey, cool. That's exactly the same as the interval from 2 to infinity. So I think that checksum anyway walks out. Nice. Okay, so I've eaten up, well, I've got enough time to introduce 2 more ideas, though maybe I'll just say them vocally and then we'll start up with that next time. So, let's just get people's intuition. What do you think? How would you get the graph of negative f of x if you knew the graph of f of x? You should flip it over the x-axis. You want to make all the y values negative of these. Yeah, that's what we go to the x-axis. What if I want to sketch the graph of f of negative x? I should flip it over the y-axis. All the x's should become negative. That seems reasonable, and that's where we'll pick up on Monday. So keep an eye on the homework assignment. Some of the problems later in the homework assignment may well be on.
Do you know when that's going to happen?
By like 2, before 2. And I'll try to even remember to send out an email when I do. And it'll only be the problems later in the homework assignment, only the homework assignment corresponding to the beginning. And if you go and do ones ahead, they'll be on the homework assignment next week anyway. So it's not like doing them will be not useful. Yeah, so you missed because I have a right?
Yeah.
Yeah, perfect. I'm going to go ahead and still do it. So, let it happen again. And a more important thing, so like these are just like 4 nice these will take one, yeah. If you try to turn in an assignment next week with that schedule, then I should take. Yeah, why were you on Wednesday?
I was sick.
Okay. In the future, just shoot me an email.
And then I had a question. Do you know if there's any chance to actively move on to math class? Because last year in high school I took AP calculus and I passed the AP test. So like I got college credit for calculus.
And definitely. Yeah, but do you have time? Talking to me is not awesome, but do you have time to deal with it like right now?
Yeah.
Okay, go up to the 5th floor.
Okay.
Go to the math department office and tell them what it is. Did you have, like, is when you take the AP exam, you're like, tell the AP board where you want your score sent to?
Yeah.
Did you have them sent you?
Yeah, but I just signed up for classes before like we got our AP scores back.
Yes, we should still, I think, you could still add, you might need like the instructor's signature.
Okay.
And if you can't get into, because you took the AP exam or BC?
The AP.
AP, so you have put counseling.
Yeah.
So you should be in counseling right now.
Yeah.
Even if you can't get into counseling right now, there is no reason to be.
That's what I thought.
Yeah.
The 5th floor of this building.
5th floor of this building.
Okay.
So go until you see elevators, take that to the floor.
Thank you.